So today I'm going to talk about one of the simplest topics in error correction, and the protocol I will describe is just the easiest thing to consider, which is just a majority rule. And first I will describe the classical version, and then I will give the quantum version using all the inputs which I mentioned in the last lecture, because there are several things which change and how you can change those things while still maintaining all the control over bounded errors. That is an important application of all the kind of things which I mentioned in the whole course. Okay. It's just a first step, but it brings out all the ideas. So, first, just the classical version. What does bit flip mean? It means with some probability zero changes to 1 and 1 changes to 0. The classical Boolean language, this is the only thing that can happen as an error, and the probability is something which will assume that it is bounded in certain sense. The code actually tells you what that bound should be. So, what is the situation in this majority rule? It's just a repetition code. Which will involve some extra work. Okay. There is no way you can get rid of the error without making some overhead. You have to always pay a price. So this requires overhead. But after paying that overhead, you want some benefit. And we will have to see what happens. So what is the repetition code? It has a very simple encoding. And this is for a 3-bit version. That every time you want to send 0, or either it is a communication, or you can also look at some data stored in some device, one for example on a disk. Every time you want to store 0 there, you store this triplet, and every time you store 1, you store this particular triplet. So the, what you call, 3-bit size makes this logic. So this is given a label. This is called a logical variable, and this is called a physical variable. So this physical variable is what actually goes in the hardware. Logical part is interpretation, which is defined as a software. So 3-bit size makes the logical variable extended, while the errors, bit flip error, whatever it is, it's a physical error, is assumed to be local. What does it mean? That yes, the physical variables are there, error will occur, but error occurs either on the first bit or on the second bit or on the third bit, no connection between them. That is the meaning of locality. The errors will occur, but the logical state is not a single bit, but it is the extended structure. So this is the assumption. You must be able to separate the scale of the logical variable and the scale of the error. So what does the code do? That the code compares the 3 bits, whether they are same or different. Okay. You have to make a distinction. It does not measure the 3 bits, it compares them. It doesn't care whether you will, when you read it, it is 0 or 1, but you want to check whether the 2 bits which are comparing are the same or different. And this, without worrying about their actual values. And this procedure is what is known as a syndrome. So syndrome is not the value of the variables, it is a property of the variable. Here the property is that whether the 2 things are same or they are different. And having known this syndrome, now you it's a bounded error. And this is what the code allows you to do. That if you tell me the syndrome, I can correct error which has magnitude or probability less than something. Okay. So now let us see how it works. Let us call the bit flip probability epsilon. Okay, so bit flip what will happen in this particular code? Well, there are 3 possibilities where this error occurs. So you can separate it out. No flip probability is 1 minus epsilon cube, 1 minus epsilon for every bit, 1 flip probability is one of them flipped, the other one did not flip, and which one flipped have different location. So there is a factor of 3. You can now complete the list without too much trouble. This will become and 3 flip. And you can easily see there is nothing but binomial expansion of epsilon plus 1 minus epsilon and various combinatoric factors, etc. Okay. Now, what do you do? That you apply this majority rule, which means I will compare the 3 bits, comparing one pair and comparing the other pair is enough, because that will tell me whether all of them are same or something is different. If they are all same, nothing has gone wrong and it's accepted. But the advantage comes in the second table. So this is accepted. If one of the bit will flips, but I compare all of them and other 2 are unchanged, and then I take a majority vote, the 2 of them are the correct ones, and I apply an inverse transformation on the first one which has flipped to make it the same. So that is this particular step, that knowing syndrome, I can correct one flip error by majority rule. So these are accepted. On the other hand, if I apply majority rule when 2 bits have flipped or 3 bits have flipped, I will get some state, but it will be the wrong one. Okay. So this is basically the essence of, so this is accepted, and in all cases inverse correction is also bit flipped. More than that, I can do this because syndrome will tell me which one has gone wrong out of the 3. If I say have gone from this state to say 100, when I compare, these 2 will say that we are matching, but this is not matching. You identify the location, and at that location you apply the correction. So it's also bit flipped at what you call reduced location. And that is essence of the whole story. How does it work? Well, you can actually give a geometrical picture which makes things easy to sort of visualize. So there are 3 bits, and I can represent them as coordinates of a cube in 3 dimensions. So this is 0, 0, 0. The opposite one will be 1, 1, 1. And I will put some label. So this is one axis 1, 0, 0. This is other axis, call it 0, 0, 1. This is the third axis, which is 0, 1, 0. And this will be the corresponding one. So it is 0, 1, 1. This is 1, 0, 1, 1, 0. And this is addition of this. This is 101. So now, what does the majority rule do? That it allows me to divide this cube in two parts, and those two parts this is a majority rule. Division. If you are in any of these states, you know the majority is going to give me 0. I come on this side. If you are in any of this state, majority is going to give me 1, and I go that side. And that is the essential of the code, that yes, I started here. One error can take me to a neighboring place, but then the code can bring me back. If I make 2 errors, then I will end up in somewhere over here, and the code will take me to the wrong state. And this is just the essence of the whole protocol. Now you can ask or quantitatively determine, what have I gained? Okay, and that is all implicit over here. The overall failure probability is 3 epsilon square 1 minus epsilon plus epsilon cube. I have an advantage if this new failure probability is smaller than the initial probability where I had no code, just a single bit, and it flipped with some probability epsilon. Okay. And this is a generic situation. The polynomials might be different, whatever appear here, depending on different codes, etc. But the algebraic structure will have this kind of feature, and the feature is that the power of epsilon which appears here is less than the power of epsilon which appears here. So if epsilon is small, this one will be even smaller. That is the point. And of course, you can check the crossover by saying that this thing is equal to that and solve this equation, whatever it is. So this is a power law suppression of the error. It implies that for epsilon less than epsilon some threshold, And in this particular case, you can solve for what the threshold is by just solving this equation. Looks a little complicated, but I will tell you the answer. And the answer is the threshold is equal to half. So if you calculate over here, this is 1 over 8. This is also 1 over 8, but there is a 3 in front, so 3 by 8 plus 1 over 8, which gives half, and that is the other side of the equation. Here, so that is essentially the story. Of course, if you make epsilon much below the threshold, the advantage will be much better because there is a higher power of epsilon sitting on the other side. Why is this enough? Because there is a very simple step I can add, that there is a error rate can be suppressed arbitrarily by recursion, which is equivalent to nested code. What does it mean in practice? That I will just tell you qualitatively, that initially the error was epsilon, order epsilon. After one step, it became order epsilon square. So here, first level takes order epsilon to order epsilon square. What happens at the next level? What does next level mean? That I will take each of these 3 bits and encode it further in another 3 bits. So the total code will look like 9-bit code. Okay, so then I correct at one level, then I do at another level. Those are the kind of nested loops which you write in algorithms, one inside the other. So next level, which will be a 9-bit code. What will we do? That error was already at this level. It will become epsilon to the 4th.
We are encoding first 0 into 9 zeros initially.
Nested. That each one of this 0 is a it will be 9 zeros, but it will go like this. Groups of 3. And what does the nesting means? First I will correct each one of these subsets, and then I will get some answer from all the 3, then I will correct the next level, those 3. And all that matters is the powers of epsilon is going up. They are of course adding more effort. From 0, their overhead is now I have to handle 9-bit. There is an extra number of variables, but the error is getting suppressed, and this is the error in the logical state. Whatever is the encoded signal, not in the physical part. The logical part is getting protected. And what this simple recursion argument tells you is, if I have enough number of recursion, I can make epsilon to much larger power, which goes to arbitrarily close to 0. Okay, provided this thing is satisfied. So here it was half, but if I started with a quarter, then it will be 1 over 16, and then it will be square of 1 over 16 and things like that. So that is enough for the theoretical proof. Of course, experimentally, how many of such levels you want to implement depends on physical availability of hardware and the amount of error you can tolerate. At some stage, okay, I can say that the error is sufficiently small and it not necessary to break my head over it anymore. Okay. That's essentially the story. And yeah.
How do we define epsilon?
It's a property of the physical system, how often this occurs. Of course, I can tune the hardware very well to make epsilon small enough at the beginning only, but it can never be 0 in any physical system. Some noise will be there.
So epsilon can depend on hardware and also on the...
Epsilon depends on the hardware, and this refined value of the logical error depends on all the codes. Yeah. The original epsilon at the lowest level depends on the hardware.
Only hardware, not on the algorithm.
No, then there is no algorithm. You are just looking at the error rate of how often this is going to happen. These are for physical variables. Now, of course, there are means. So this construction is or this protocol is sufficient for looking at communication or memory data. But I have implicitly taken something for granted, and that is, but errors can occur even in encoding initial I assume that I can construct this from here, but that process also has an error. Suppose it made something wrong at the beginning only, then the whole algorithm is not going to work in the same manner. It can occur in this syndrome extraction, where I said that I compare the bits. Well, that procedure also can be faulty. This is all being done by some component in the hardware. Everything can go wrong in general, and it can occur in this inverse correction step also. The algorithm tells you correct it. Whether it occurred or not, I don't know. It's the hardware job or the fault. And in this description, I will take things for granted that I have not bothered about this. But in a realistic scheme, you have to take into account those as well. So these also require some protection. And the solution for this is the signal is kept encoded throughout, all the way from the initial part to the output which you want to read at the end. At no stage I will break up the code to extract the intermediate state.
Means we have applied no error correction. Means we have applied no error correction, neither some error occurred.
Error correction is applied, but it's applied on the encoded state. But the instructions which will be part of the algorithm, they will also act on the encoded state. This is assuming that the data is sitting in memory, but now I have an algorithm which will manipulate all the intermediate steps. Where are they going to act? So the algorithm, the intermediate those steps are going to act on the logical states, not on the physical one. You have to find a logical gate which will transform whatever that state is. It will be a complicated state like this, but you have to find what will be the logical operation of the algorithm on this particular state. It's not just going to be one bit operation, it can become complicated operation, whatever there may be. And that requires work. You have to redesign your codes or software in terms of gates which will act on these logical states. And that is the overhead. Well, it will suppress this value of epsilon, which is given by this particular threshold, because there are errors at many places, and consequence is that the amount of error you can protect against, which is given by this threshold value, its value goes down. Okay, here it may be half, but then you want to protect again all the states, well, it may become smaller than half. But the overall structure will remain that this power series of suppression will survive.
Before operating each intermediate algorithm steps, we need to do error correction step.
Yeah, error correction steps will be there. Error correction steps are implemented on the whatever the physical state is, but you don't extract the logical value after performing error correction. If it went from 0, 0, 0 to this state, error correction steps will just bring it back to 0, 0, 0 and let it remain 0, 0, 0. You're not going to reduce these 3 zeros to original one. And then the operation, whichever you need for the algorithm, will act on this remaining 0, 0, 0.
So this is a multi-stage error correction.
Hmm?
Throughout the algorithm,
Throughout the algorithm, you have to use error correction. So yeah, this is the philosophy. It's all classical in this example, but these concepts go over into the quantum domain with some modifications. Okay, and those I had listed last time. I will now convert it according to those rules. But before that, let me give some practical examples. Okay, so our standard computers based on silicon chips, they have some value of epsilon. Do you know what it is? Yeah, so this is a the physical error rate on each bit, or whether whatever you have recorded in a hard disk or a CD or whatever it is, the error rate is about 1 part in a million. Things are there. If you apply this majority rule code, just one level of it, then this argument tells you that it will become of the order of square of this 10 raised to minus 12. Is it good enough? Well, not quite. The reason being that our algorithms are running at the clock speed of the computer, which is in gigahertz, which is 10 raised to 9 per second. So multiply by 10 raised to 9, that number 10 raised to minus 12, you get about 1000. That means the computer will crash every 1000 seconds. It will give wrong answer. That is not good enough because 1000 seconds is about 15 minutes. Too frequent for our practical use. You need something more. So there is a something which is acronym for this thing is called which was became popular some initial days of this VLSI design. It gained by this label. It stands for single error correction and double error detection. So if there is a single error, it will correct it on the fly by whatever it is code. If there is a double error, it will be able to detect it, but can't do anything. It will just stop. The program says that I cannot work anymore. Correction, double error So if the error is 1 part in a million, this is not good enough. So better codes are needed. This number is not good enough. Either you make this number small, then this single error correction will work, or otherwise you find some better alternative code where this suppression, instead of just being square, is larger. Maybe it is a multiple layer or a different code where these things can happen. But this is a story which is buried inside all the silicon chips which are in our computers. There is another important process, and that is the biological fact of copying the genes. There are too many mutations, the whole thing will go wrong. The errors are there. So that also has an error correction procedure. We don't know how exactly it works in great detail, but enough evidence that DNA, while it is making it a copy, it corrects errors.
It makes perfect copy. It makes perfect copy of each.
Yeah, so the point is if there are too many mutations, there is some epsilon, whatever this rate is, and I will tell you what that chemistry gives. Its number is about 10 raised to minus 3. That is not good enough, because if you look at the length of DNA, how many letters it has in every cell, the number is in billion, 10 raised to 9. And you observe how many wrong copies are made when the whole genome is copied from one generation to the next. That error rate is about that 1 part in a billion. So there is a machinery inside every living cells. It does this error correction by all interaction of molecules, proteins, whatever checks it has to make. But this 10 raised to minus 3 is suppressed down all the way to 10 raised to minus 9. If that is not true, the mutation number will be so large that the next generation won't survive. Because it's an information, it has to be faithfully passed on. Of course, zero error rate is never achieved in practice, but assuming it is sufficiently small, you can tolerate it. Okay. So these are some practical numbers. It basically tell you how hard you have to work, okay, to get numbers down. Yeah.
The length of the DNA is 1
Billion.
So 1 billion times 10 power minus 9 is
No, so that means
that would be every other.
no. If you look at actual genome, for example, the human genome, the error rate is. This number is there. It comes from that, but the human billion, I think, is a 3 billion base pairs. Okay, and if you now assume Well, again, observe experimentally when a cell makes its replication, how many of those 3 billions are faithfully copied, and I think the number is probably about 30 errors are observed. So it may not be 10 raised to minus 8, it may be 10 raised to minus 8 to 10 raised to minus 9, something in that range. But it has to be brought down to that particular level. Of course, these numbers vary from organism to organism, whatever it is, and bacteria might behave differently than what goes inside human cells. The reason being that the bacterial genome is much smaller, the human genome is much bigger, and so we have to find out what are the corresponding error rates it can tolerate and how sophisticated the correction machinery has to be. But these are representative numbers. Okay. So it's a non-trivial story. Things are not that easy, even in the classical case. And now we ask a quantum case. And you have to reconstruct all these steps without violating the rules of quantum mechanics. Okay. Start at the first step itself. This is basically making 3 copies. No cloning theorem says I can't do it for arbitrary states. Okay. What is a 0 or 1 will actually be a superposition. So what you need is initial state will be something like this. A and B are unknown coefficient. Here it was either 0 or 1, but whatever it was in a particular message, it could have been either of the 2 values. Quantum case, the generic state is like this. And how do I construct this extended state? I can't just make a copy of that because it's not allowed. A and B are unknown as far as the code is concerned. And so this is the encoding. And the answer is encoding is this particular combination. Okay. It is an untangled state. This is and it is different than what copy will do. A copy will just make 3 times this. That 3 times is basically just a tensor product structure which we have used all over the place. But the encoding uses this and not this. This is not allowed, this is allowed. And how it is allowed is very easy to see. This is all the kind of circuits which we have used, immediately gives you an answer that the state produced by this, just to simple control not, they are just going to copy the first bit into the other location, is this. Okay, these two were initially 0, 0, but if this has a 1 inside it, they will become 1, 1. So this is the first feature. Okay. And it says that I cannot construct this, but I can construct that. The second step after constructing this syndrome extraction. And what it has to do is compare the 3 bits without reading their value. And can I do that? Well, yes. How do I compare? Is binary addition. If there are 2 values x and y, if both of them are 0 or both of them are 1, then I can say that the 2 variables are the same and the answer is 0. But one of them is 0 and the other one is 1, the answer will be 1, and I say the 2 bits are different. Remember that we are not evaluating x and y, but we are just comparing them. Okay, so now what do I have to do? Well, can I evaluate this? No big problem. A control not is again the same operator which allows you to do binary addition. So all I need to do is, well, I have to add this syndrome bits. So I take this 3-bit state. So this is the state. And then there is a ancilla. And all I need to do is I have to make 2 comparisons. So suppose this thing is whatever this value is. Let me call it x, y, and z. I make this 0. This one is also 0. And this will now become x plus y, and the other one I can make y plus z. And if I now measure this, remember I am not doing anything to the state part. So measure, and then I can apply the inverse operation. What does it tell you? If these values are zeros, nothing has gone wrong. But if one of them is 1, something has gone wrong. And then I have to do something. Well, what is that particular step? If it is 1, do something to the code. Another control not. You have to flip. So we can take this line, and this is a correction. So what do I need? So I have to, well, you can write it down. There are 3 possibilities. If x and y is 0 and y and z is 1, then there is an error and I have to flip z. So, okay. Let me do the easier part first, and then I have to do some other jugglery, but that is a little complicated. So fine. I can draw a circuit. It's all reversible logic, not very complicated than that. So suppose both of them are equal to 1, and that means the variable y is wrong. Okay, x and z are equal, and that can be done by what is the Toffoli gate. It will flip the value of y when both of these are equal to 1. Then look at the other cases. Suppose this is 0 and this is 1, which means z is wrong and have to flip it, but it has to be flipped only if this one is 0 and this is equal to 1. So I can use it as a Toffoli gate, but the way the Toffoli gate is defined is a little different. So I can use the same notation, but to take into account that this value is 0 and this value is 1, I will put a not step in the middle. It looks a little bit cumbersome, but yeah, these are all notation dependent structures. You have to put everything. So if this came out 0, this not will make it 1, and under these 2 conditions, this bit has flipped. And then the other case, third one happens to be when this is 0 and this is equal to 1, so I have to reset this to put another knot, and then another Toffoli gate will restore the first variable. So this is so this is the procedure, both the syndrome extraction and after extracting the syndrome, this is the inverse operation. But the point is it will get back to the original state, and what you note is this is the number of steps involved in terms of all the logic gate is larger compared to whatever was over there. Here I could just do simple bit flip and simple comparison. The quantum logic circuits will require so many extra gates, and this ancilla is the place where the syndrome is stored, and which makes epsilon threshold smaller. Because you have to take care of errors occurring in various places. If there are many operations, each one of them can have some error. You just have to add it up. And that essentially describes this particular process. But yeah, you need to go further. That this is not the only thing which happens in a quantum signal. I only corrected the bit flip part, but there are other errors. E.g. sigma y and sigma z operators. And here, bit flip goes to sigma x. And it's not enough to just correct bit flip, but the other stuff is also there. You need to figure out how to do it, and that means you can have multiple of such procedure. One will correct sigma x, other will correct sigma y, the third will correct sigma z. Actually, you don't need a separate thing for sigma y. If you correct for sigma x and independently correct for sigma z, it is enough, because what sigma y will mean is that there will be an error correction in the first part and also in the error correction in the second part. It's a double error. You can count sigma y as a product of sigma x and sigma z. So if you have two parts of the circuit, one corrects x error, one corrects z error. So correcting sigma x and sigma z errors independently is enough. You would make one circuit for this, another for that, and the error actual physically what happened is sigma y. Both of them will do the correction, and that will get you back where you wanted. So that is again an overhead, so this threshold will become again smaller. You have to take care of all those operations, and moreover that this caveat of where the error occurs remains. There could be error in this initial encoding itself. There could be all the errors in this syndrome extraction with this, all these control gates and the state of the ancilla, they can also be disturbed. And then there is this final thing which said you measure and you apply the inverse operation. Well, even your measurement can be wrong, and then this thing will produce something wrong. So all those caveats remain. And to go to this particular stage, so which means the fault, this is the label which I mentioned last time. Fault-tolerant computation and which means correcting errors at every stage while keeping the logical state encoded. The same argument which I gave over here at needs this value. Here it was a very simple calculation. I could get number like half. And this number is something which depends on the codes, etc. to some extent, but it is of the order of 10 raised to minus 4. There is a lot of overhead which will bring this number down all the way from half to something like 10 raised to minus 4. And that is now the challenge to the hardware, that can you design these qubits with error rates less than this.
This challenge threshold is achieved by multiple layers of encoding.
Yeah. Now all the layers, all the variables which you add, you have to count how many combinations will make things wrong, and this, what it does is, there are this simple things like here it was just a binomial coefficient, but this number goes up when you add all the things. It's true that epsilon will go to epsilon square, but what the coefficient of epsilon square is, it matters. And that coefficient becomes sufficiently large, which makes that you have to bring down. So here epsilon going to order epsilon square remains valid. But by putting the number like this means that what is the coefficient of epsilon square? You have to actually figure it out for the particular hardware implementation of such an algorithm. And this is a big enough challenge at the level that none of the quantum processors on the market have been able to implement even a simple thing like this. Whether it is IBM or Google or Microsoft or whatever it is, they can't do it. Or rather, you can program this circuit, no problem, but the threshold is not small enough. And if you are above the threshold, with all this extra stuff, the error will actually go up. Yeah, so this poly error can be corrected in 2 steps. Okay, there is a circuit which here is like sigma x. No, the generic state, it's a qubit state. And the error, here I have only talked about the bit flip error where 0 goes to 1 and 1 goes to 0. But the other operators are also there in the logic which will change the phases of this A and B. And they also have to be taken into account. Those are the other polymetrices. There are multiple directions. Qubit has many things the way it can change compared to just an ordinary bit which only can flip.
And everything sigma x and sigma z is enough.
Yeah, so that is, if I now make one code which removes a sigma x error, another code which makes sigma z error, And the conversion is not complicated. All I have to do is use the Hadamard matrix. So I convert from X basis to Z basis and correct the error, the same thing. And then I apply the inverse Hadamard again to recover. But the point is that what will happen if the error is sigma y? I can write the sigma y is equal to product of sigma x and sigma z. So it's equivalent to saying that the error will be corrected in the first part of the circuit and it will corrected in the second part of the circuit also. And then you don't have to deal it with separately.
You're saying sigma y can be written as product of sigma x and sigma z? Are you saying that?
You can do it anywhere. Multiply two polymatrices, it will give you the third one.
So unless we make a hardware whose threshold is
Yeah.
whose this is
This code, I mean, you can implement it, but it will end up increasing the error. Then it is of no use. You must go below this value for it has to give you some advantage. If there is no advantage, then you won't do all this hard work.
In classical case, we got a threshold of half for 3-bit case, 3-bit.
Yeah.
And that is also changed by the other errors in the classical case.
Yeah, so when you do all these things, this half also will go down.
But in the
Quantum case, there is a lot more.
in the first step only, we have got.
Yeah, first of also, there are so many different operations, you have to count all of them. How many logic gates are there?
so if we import with 2 bits, then this threshold will go down.
Yeah, this is just for looking at 1 qubit protection. If you have a multi-qubit register, well, you have to take care of all of them and find a scheme for extending it. As I said, this is a whole business. There are now books written on error correction algorithms, and there will be a course next semester in the EC department on this quantum error correction. All I'm saying is that this is an introductory description of what is involved. Principles we have seen and I have illustrated how you can apply. But now if you ask for a more extended version, well, there are lots of complicated structures you have to add.
The error correction happens in the physical.
Yeah, so these steps have to be implemented on the physical states, whatever they are. But after doing the whole computation from the output, then you will project back onto the logical part. All the intermediate steps are all on the physical components.
So this is what the below of epsilon, below of epsilon.
Yeah, this remains valid, but the coefficients which appear in front, they are hidden in this notation. Whether it's epsilon square or 1000 epsilon square, I don't know. The notation keeps it the same.
But this is for the logical, after the converting into the logical.
Yeah, after converting to the logical part. Yeah. So yeah, that is about as much as I want to say on this topic. Now, if you have any other questions about many other things which went on in the course, you can ask.
In the last class, we went over the about circuit models and topological systems. So, in circuit models, individual components can survive either.
Yeah, that is the number I quoted. Topological model is a different kind of implementation. It is not just this.
In topological model, we cannot see topological system as individual components or individual gates.
Yeah. You have to look at the topological encoding. It is not just some simple thing like that. It's much more complicated. And the properties which are used as syndrome, they are also more complicated. You have to, study those systems first about the way the physics description of that is, and then you can figure out how are you going to encode the logical signals inside that system, and then how you will be transferring them, protecting them, looking for syndromes, etc. But the advantage there is that this number can be made larger.
Is there any physical realization of topological quantum system?
Not yet. Theory has been worked out. People have to actually make any of those things. There is one question which Mayank had asked in the Teams account, and he is not here. So, I can answer it, that is fine. It regards this question of how do you evaluate this computational complexity. And the important point there is that you have to have an algorithm that should not hide the answer inside it. Simple example is a factoring algorithm we looked at in detail. And suppose I want to construct some general purpose structure, and I can easily put in the instruction that if the number is 15, the factors are 5 and 3. Just one particular statement it will execute, and then I don't have to work the rest of it. The problem with that is it will work for that particular specific case. But what if the number was something else? It won't work. So the purpose of this thing, it should work for generic inputs, not only for some particular instances. If you are given a particular instance, you can easily design some quick fix to solve the problem, but that is not the purpose. Okay? There are many different inputs possible, and the algorithm has to work for all of them. Of course, there are variables. So, what I mean by generic inputs? So, in particular, both input size and output precision they are variables. Input size can change. How much is the number in terms of bits that you want to factor? output precision can change if it's not a Boolean function, but it is a function involving some real numbers, and can say I want to evaluate pi to so many decimal places. So these numbers can change. And the point is that the algorithm should be able to tackle these changes. Okay, once I say that it works for 10 bits, and I ask what happens if it is 11 bits, what do? Do I construct the algorithm all over again? Well, if I have to do it for every possible situation, it's too complicated. So there is a concept of what is known as a uniform circuits. They allow you to generalize algorithm size, e.g. n bit input to So these are the kind of algorithms which have a systematic procedure, which says that if I know how to run it on n bit input, I can construct the n plus 1 bit input from it. And one of the common mathematical procedure for is induction, which says that I know how to do it for n, then I know how to do it for n plus 1. I don't reinvent the whole machinery all over the place, and that kind of structure is given this name, uniform circuits. So when you search for complexity, you keep this in mind, that algorithm should work for varying sizes of the input and output, and when I vary the size, I go from one size to another by a procedure of some type. Induction is an example. So that is the kind of algorithms which I went through in the whole course. This was always possible. Okay, when I say n bit, I wrote down some circuit, I all had a immediate description of what if the circuit is n plus 1 bit. I can generalize, no problem with that. Then there is another feature which is needed, is for bounded errors. That in general the algorithm may not succeed all the time. And what we want is, well, if it doesn't succeed all the time, but it should succeed with error rate which is sufficiently small. All this epsilon business or whatever it is part of the story. So now what is a non-trivial feature in that? That epsilon should remain bounded while I play around with all this structure, and this error rate epsilon and one of the example is in the same notation is number of bits going to infinity. So even if the size goes to infinity, this value should remain finite. It cannot blow up. Okay, if error rate is going to blow up as you increase the size of the circuit, that is not good. And this is you have to take care of. Now there are various trade-offs in this bounded errors. That what do you mean by the error rate? So sometimes the error rate is the worst case. Situation, the one which is likely to fail with the largest probability, and sometimes it is just the average case situation. You have many different inputs. On some of them it works, some of them it doesn't work. You average over the possibilities and find out the average rate. So these are different criteria. Okay, the worst case can be much harder to tackle than the average case situation, but it depends on the application. Many times you are happy with the average case situation, which says that, it's going to fail. There is a tail of the distribution where the error rate is very large, I will ignore it. Okay. So this is some practical trade-off. But if you look at literature on this computational complexity and in particular how they deal with bounded errors, you will find both the kind of algorithms. Some of them insist that it should work on the worst case scenario. The errors should remain under control. In practice, most applications are happy to be living in this average case scenario and give up some specific instances because you don't have the luxury to wait indefinitely for getting the right output. So this is something about computational complexity which Mayank asked, and I kind of told him immediately in the conversation, but it's a detailed description of how you look at the problems.